All right, so it's now Monday night. Time flies, and it's a wonderful life, but there's always a lot happening, and there are new tasks which are given to us, and some of that stuff, if we know how to do it well, we could do it quickly, and other things, if it's new to us, it takes us time. And statistics is a little bit new to me. And so for one of my other classes, I could sit down. I've taught that class for decades. I could sit down and just give those lectures. But with statistics, I have to really think about it. And so it doesn't go as quick. And it's taking a lot of time to put all these lectures together and to try to convey this in a way which, to try to understand it in a way which makes sense to me. And when I understand it in a way that makes sense to me, then I'm able to convey it in a way that hopefully makes sense to you. But anyhow, it takes time, and now it's Monday night, and it's 10:30, 9 p.m., and I would love to get through all of these 68, holy majoli, lectures, slides, and we're on 23. We'll see what happens. So we're going to learn about one-tailed hypothesis testing for the population mean when the population standard deviation is known. We've already learned about everything else in the previous videos that you've watched, including just the most recent video, which was, type 1 and type 2 errors. And so now we're going to learn about doing one-tailed hypothesis testing for the population mean when the population standard deviation is known. And the best way to learn about this is just, I think, to start out with an example. And so everything that's important is in yellow. And I'll read through it, but the FTC is the Federal Trade Commission, FTC Gov, right? And Federal Trade Commission, protecting America's consumers. And so, if there's fraud or scams or identity theft, you can learn about these things here. And FTC.gov, .gov means it's official, but like these people monitor, companies, right? They have a limited budget, and so they can only do so much. But that's why they exist. And so let's say that FTC wants to check Hilltop Coffee, Hilltop's claim that its large can of coffee contains 3 pounds of coffee. The FTC director wants to perform a hypothesis test and with a 0.01 level of significance to check Hilltop's claim. So 0.01 level of significance would be, and if we remember our vocabulary, so I'm just going to launch this into a new window and then bring this window over here, and I'll put this one here, and we'll put our vocabulary over here on the right? But they want to perform a hypothesis test with a 0.01 level of significance. And so that level of significance is right here, and that's the alpha, which means we're going to have a 99% confidence level. And suppose the random sample of 36 cans provides a sample mean of 2.92 pounds. Previous FTC tests show that the population standard deviation, the only reason these are in boxes as opposed to being highlighted is because those are actually images. The way this presentation has been created, people just created images for some of the stuff and just put the images in there. So the only thing I could do on that is put highlighting around it, because if I fill it with yellow, it just turns everything yellow. So there's no difference between how those are highlighted, though. It's just sort of out of necessity they're highlighted differently. So previous tests showed that population standard deviation and population standard deviation, I'll also highlight that because that's part of the phrase. But I highlighted it with the wrong stuff. I need to do it with this one here. Highlight, marker, yellow. There we go. Can be assumed with a known value of population standard deviations equal to 0.18, and also show that the population of filling weights can be assumed to have a normal distribution. So when we look at all of that, and I'm going to come down here, and here's our example. First thing we have to do is come up with our hypothesis. And so our hypothesis here is like, I'm asking myself to come up with this hypothesis. I'm asking myself, what is the current state? Like, what is the state of reality? Because when we develop hypotheses, we want to, for me, I like to think about the null hypothesis. Like, nothing's changed. It's the current state. There's no change. It's the status quo. So what's the current state? What's the status quo? The status quo is this claim that coffee contains 3 pounds. And does it matter if it's precisely equal to 3 pounds or if it's 3 pounds or more? And so in this situation, if they're putting 3.2 pounds or 3.1 pounds into a can of coffee that's supposed to have 3 pounds, like everything's good. You know, like it's 3 or more pounds is the way I'm thinking about that, because consumers in the FTC are not going to have an issue if they're saying you're getting 3 pounds and you actually get a little bit more. No big deal. Right? So the current state, my null hypothesis, is that, like, you know, the population mean is going to be greater than or equal to 3 pounds. And my alternative hypothesis will be that the population mean is less than 3 pounds. And so here is the null and alternative hypothesis. And this is in alignment with, you know, this is what the textbook came up with too, right? But the null hypothesis is that the population mean is greater than or equal to 3. And remember, equality is always only going to be in the null hypothesis. And that's just at a different pay grade than I'm at in statistics. Why is it only equality only in the null? It actually kind of makes sense at a level that I'm not going to try to attempt to articulate right now. But that's the null hypothesis, and the null hypothesis in statistics is where you include equality, if you're going to include equality. And then the alternative hypothesis is that it's less than 3 pounds. And so this is known as a one-tailed hypothesis test. Because when you think about this, and let me just find this guy right here. So I'll move up to this one here, and I'll grab this, and I'll bring it on down. I'll bring it on down. When you think about this little guy right here, this bell curve, and let's put it right there just to talk about it for a second. So this is what we did in chapter 8, where we had some probability. And this was, and if we look at our definitions, right, this was our confidence interval, right? Sorry, yeah, the confidence interval is here. There's the mean, and then we had a plus or minus on each side. And then our confidence level, our confidence coefficient, was this amount in the middle. And then our level of significance, our alpha, was divided between these two tails. So this was a two-tailed test. That was a two-tailed test. And what we're going to do here is we're going to do a one-tailed test. So one-tailed hypothesis testing. Now, why are we going to do a one-tailed test? The reason we're going to do a one-tailed test is because we're looking at something where we want to see if we're below a certain amount, if we're below 3, right? We're not looking to see if, like, hey, is it some amount on both the left and right side, which would be a two-tailed test, but we're looking to see if it's like gone too low. If it's gone too low. So we got to see if it's like greater than a certain amount or less than a certain amount. And we're looking for it to be greater at 3 or greater than 3. And so that means we don't need to worry about both tails. We're really only worried about one tail. And the tail we're worried about is this tail here, this lower tail. Because when we calculate some test statistics, and we're going to see this in a second, you know, we're going to see, do we fall in this region here, in which case we're going to reject the null hypothesis, or are we in this region here? This is like 1%, right? 1% is this way, and so with 99% confidence, that will be in here. If our calculations we come up with land in here, then everything's good. But if they land here or left, right, then that 1% is no good, because we want to go to the 99% confidence level, right? 0.01 level of significance. Our alpha is 0.01. That's our level of significance. It's right here. And so our level of confidence, our confidence level is going to be 99%. So there's that question. And if we look at that question, we could come up with all of this right here. And so I'm going to go to this one first, sorry. And they're exactly the same. This just has the next level of analysis. So we're going to look at this first from what we did in chapter 8. And we'll just create a confidence interval based upon this data that we have. And we'll just kind of look at that confidence interval. And I'm going to show you a graph I drew. I'm not sure it's correct because, again, I didn't get my doctorate in statistics, and I'm new to statistics. It's the second semester I've taught it. But I took it as an undergraduate. I took it as a graduate student. And I feel like I've got a pretty good hold on it, but I'm still catching myself making some mistakes. And so I'm just letting you know that this graph might be one of those mistakes, or it might be right. I don't know. So if you have insight into it, comment down below and let me know. But here is, and I'll always be straight about what I do know and what I don't know. And if I'm unsure about something, I'll let you know that, hey, this needs some investigation. So here we have all this information. So our hypothesis null, the null hypothesis is that the population mean is greater than or equal to 3. The alternative hypothesis is that the population mean is less than 3. Our level of significance is 0.01, which means our confidence level, aka our confidence coefficient, is 0.99. Our sample size is 36, right? 36 scans. Our sample mean is 2.92 pounds. Our population standard deviation is 0.18, okay? And so with all this information, we could use this formula from chapter 8. And that formula from chapter 8, this is going to be our margin of error over here on the right, right? So we're going to have our sample mean plus or minus some margin of error. And that margin of error is the plus or minus part, right? Margin of error is the plus or minus part right there. And what the margin of error is made up of, the margin of error is made up of the z, which is the number of standard deviations, and then what is the quantity of the standard deviation. So this is called the standard error, this part right here. And I think of it as like the standard deviation of the samples, right? So when you have your sampling distribution, the standard error is the standard deviation of all of your different samples of some characteristic of interest, like the mean, right? This is going to be the standard deviation of that, and this is going to be how many standard deviations we want. So that's going to give you the plus or minus some amount. And if you remember going back to our formulas, and I have to go over here to get our formulas. And I think that's it right there. And I'm just going to choose show more options and go to open with, man. Where's my open with? Open with, and I want to open it with photos. There we go. And so if you remember what our z-score is, it's the number of standard deviations of some point from the mean, right? So at some point we have here, it's the number of standard deviations of some point from the mean. And when we multiply that by, the standard error, which is like the standard deviations of the sampling distribution for some characteristic of interest, like the mean, right? Then, or a proportion, then that's going to give us the margin of error. And this is the standard error, and this is the z-score. So that's chapter 8. And when we do that calculation, we get 2.92, because sample mean is 2.92. And then we get 2.575, and we get 2.575 here because our z-score, if we have a confidence coefficient of 99.99, so 99%, our level of significance is 0.01. And then if we do like a two-tailed test, 0.01, and so we're just going to do a two-tailed test on this because that's the way we did it in chapter 8, and 0.01 divided by 2 is 0.5%. And so if we come down here and we look at what is 0.5%, right, that's going to be like 0.995 is 0.5%, right? So if we have 0.05 in the top tail, so our top tail, and again going and looking at this picture right here, so if our top tail, let me just make that a little bit bigger, I don't want to crunch that. But if our top tail is 0.05, that means 0.9. If this is 0.5%, this means 99.5% is from here to the left. From here, right, to the left. Because we got 0.5% here, that means 99.5% is from here to the left. So here is 99.5%, 99.5, 99.5 is right here. So here's 49 and 51. So it's going to be right there between those two. It's going to be 2.575. And if we go back and we look at that calculation, we have 2.575. So that's our z-score of alpha over 2. And then we have this, which is our population standard deviation, 0.18. Divided by the square root of n, which is 36. So when you do that calculation, our interval, and again, I'm still getting the terminology myself, our confidence interval, the range of values will be here. And we'll have a 99% confidence level, confidence coefficient, that the population mean will be within this range, right? based upon all this data, 99% confidence level the population mean is within this range. Well, when we look at this, here is this hypothesized distribution of what the coffee can. So based upon this question here, which is right here, right here, right here, right? This is the hypothesized distribution of what the coffee can should be, where the mean is 3, and we have 3 or more pounds. And should be even tighter than that, right? Like we shouldn't really have much variance. So I should have maybe made it like really up like this. And then here's our sampling distribution from all of this data from this, survey, this study that the FTC did, where the sample mean was 2.92, and then our interval, our range, and I'm just looking for the correct terms. So our confidence interval, our interval estimate, which is the range of values, confidence interval estimate, which is the range of values, right? This confidence interval confidence interval estimate goes from here to here. So this is like 99% confidence that the data is going to be between 2.84 and 2.99, that the population mean, based upon this stuff here, the population mean is going to be between these two with 99% confidence. Well, knowing that, right, we could see that the desired way that, things should be when they're claiming that there's 3 pounds of coffee in each can, that is outside the range. So already just kind of looking at this, understanding what we learned in chapter 8, we could say, you know what, they're not filling it up to 3 pounds. With 99% confidence, the population mean of how much they're filling those cans is between 2.84 pounds and 2.99 pounds, with a sample mean of 2.92, all right? And so they're underfilling their cans. So that's using what we learned in chapter 8. In the next video, I'm going to continue this, and we're going to learn two new methods for also proving that these cans are being underfilled. And they also build upon what we learned in chapter 8. So it's pretty similar to what we did in chapter 8. We're going to have one new formula, and you can see here that, right, when I did this calculation here for the way we did it in chapter 8, that was the formula we used in chapter 8. We're going to learn this new formula right here, and this is introduced to us in chapter 9. So we're going to see how to use that. We're going to see that in the next video, just because I like to break the videos up. So see you in the next video.